last part. I now want to tell you how to simulate with what we discussed so far. I actually want to focus on the pressure a bit. So this is our physical model, right, Navier-Stokes. We can leave out this part because we have our particle viewpoint. And I mentioned that we also can neglect this for now because we just need to make sure no particle gets lost, then we conserve the mass. Now we're left with computing the force terms on the side, and I will focus on the pressure in the following. The viscosity is actually relatively similar, I'll point that out in a moment. And gravity, this is easy, we can just add it on top. Yeah, a note about the notation. In the following, we'll actually write A of xj as the sum over all the contributions times the weight of the kernel. So we leave out this distance part because that's actually common to all the kernel evaluations. What typically matters is how we evaluate the different contributions here. Yeah, so for pressure, what we need is a so-called equation of state. It typically looks something like this here, and why this is needed is we basically need to convert the density values that we have on our particles. So remember, those we get by only evaluating the mass with the kernel weights. We need to turn this per particle density into a pressure. You could just directly scale it, you could have a linear relationship, but turns out that's actually not a good idea. It's typically nonlinear, and this is a popular formulation. So first we actually choose a rest density, rho 0. This is something we just said. So this is our kind of ambient density. And right, if the particle has exactly that density, then you see this fraction here actually gives us a 1. And then all the rest, the 7th power, will not change anything, right? So for a density of rho 0, we have a 1 here. Then we subtract 1, leaving us with a 0. And effectively, that means if everything is in a rest state at the rest density, then there is actually no pressure. However, if we are above, then you can imagine we have something larger than 1 here to the 7th power, so we actually very quickly escalate into the positive direction. And vice versa, if we have something less than the rest density, then this will be very quickly much smaller than 1. We're subtracting 1, and then we actually get something negative. So this is evaluated for every particle individually, right? This does not depend on any sum or any neighborhood. As soon as you have the rho I for a particle, you can calculate its pi value. And now we turn to the kernel to evaluate our pressure gradient. So remember, from our Navier-Stokes model, we actually need the direction where the pressure goes down, where it decreases. So the negative gradient, on the slides before, we typically had minus nabla of p, the negative gradient. And this we can evaluate with the expression down here. So we have the gradient of a kernel function, as mentioned before. Then we don't need to deal with the gradient some other way. This is our regular weighting. And now the slight trick that we have here is that we actually take not just the pressure of one particle, like we had in the regular attribute evaluation, but for the pressure we now take 2 of these and average them. So in this case, it's actually written for a particle j. So if we want to know for particle j, how does a neighboring particle I influence it, then we take the pressure of j and I and we average them. The great thing about this is that for I to j and j to I, in both cases we'll have the same magnitude, right? They have the same distance, so this will be the same. They'll just have opposing directions, but this actually nicely conserves momentum and is symmetric. So this term for two particles will be the same in both ways, both directions, from I and from j. Yeah. Right, so the rest density you can, for example, compute in the beginning of a simulation or set as an external parameter. Now, the next force that you would typically compute is the viscosity force. This I don't want to go through in all detail. It's actually somewhat similar. In this case, we're looking at a difference of velocities. This is basically this friction component that I mentioned before. And then we have a very similar overall evaluation just with the second derivative of our kernel function. And then this is typically multiplied with some viscosity constant for scaling. As a last point, these two steps here is something we haven't discussed so far, but turns out it's actually something that's quite useful in SPH simulations. This is a bit of a new effect that comes in when we have two fluids. If we have something like air and water, and they have an interface, then, as you might have seen or experienced, water actually tends to form spheres or pull in, form droplets due to surface tension. And we can also simulate that with SPH. This actually typically happens with a kind of intermediate step. So for that, we first take a color field, so called C for example, that we interpolate as usual with our kernels. So note in this case how it's defined as color is we actually interpolating an attribute of 1, right? Basically, you have a 1 in here, or you could imagine that the Ci value for all particles is essentially a 1, and then goes in here for our evaluation. And this gives us a constant function interpolated with our kernels. You can imagine it basically gives us, right, it gives a high peak where the particle is and then falls off. Right? Just a smooth highlights for all the particles. And then as a second step here, we compute the surface tension as the curvature of this color here. Here the color goes into this equation. Take the second derivatives, which is, you can think of as a kind of curvature, and then let this work in the normal direction along the surface. So the details of this won't matter. This is a bit more of an advanced step in SPH, but I want to briefly explain how that works. This basically models the effect that in a normal fluid there is a kind of molecular force that essentially pulls in the molecules into the fluid. So you can imagine this as right, basically acting on the side of the particles and making sure that the particles are really surrounded everywhere by fluid. So if any one particle at the surface here would move out, it would actually see even less of a neighborhood here and then experience a corresponding force into the liquid, for example, to pull it back in. This has some interesting properties because it's effectively very geometric. It makes the fluid form minimal surfaces, minimal area surfaces, sorry, for a given volume. And right, what is the which shape has the minimal surface area for a given volume? Can you imagine what that looks like? It is actually a sphere. The sphere is a perfect shape in terms of minimal area, and the surface tension actually then also works towards making everything sphere-like, unless we have some other internal forces or so that perturb the spherical shape. Yeah, and that also in practice actually, if we have a strong push, imagine we are strongly pushing from the inside for some reason, and something actually moves out fast enough, that has a nice effect that it kind of breaks off and forms a smaller droplet. So what can be useful here for SPH simulations is that we have these particles in our simulation, and the pressure actually makes sure that we don't have too many particles that pile up. It kind of pushes particles out of each other. The viscosity forces, that's this friction, that basically makes sure that the particles don't move too dissimilarly. But there's nothing that keeps the particles in one spot like we expect from a normal liquid. And that's actually what this surface tension force can do. Can help to kind of control the particles a bit and keep them together. Yeah, and there actually surface tension is a neat topic because there's some really fascinating effects that develop from it. So I just wanted to show this in a movie here. So here is a nice slow motion movie of droplets forming. And here is the experiment. Looks not so impressive so far, but wait until you see the slow motion version of it. Okay, this is 2500 frames per second. Surface tension can actually be so strong that it lets the drop bounce back from a surface. And at some point, due to impurities, the droplet will still break up and dissolve. So that's going to happen here in a moment. But surface tension is strong enough to pull together the remaining liquid. Now we have a second one. And nicely enough, this also now got absorbed, but there's still a tiny bit left, and even a fourth tiny droplet forming afterwards. And right, this is now bouncing around. I think it's even yet another one. Yeah, so this is a good example of surface tension. Another pretty cool one that is very unintuitive are these almost bone-like structures that form. So here, can I pause this? In this experiment, all that we have are actually two crossing streams of liquid. So you can imagine they're coming from the top, and they have different speeds. And now as the speed becomes lower, these two streams move closer to each other. And there's some really fascinating patterns here. It's called the fishbone structure, where droplets fly out on the side, form droplets, and then detach in this very regular fashion. Right, and all you need to do here basically is to have two jets of water and vary the speed, the flux of water. Yeah, there is a YouTube link here if you want to check this out for yourself. All right, so back to the overall algorithm. So let's summarize how SPH would proceed in one step of the simulation. One topic that I've not mentioned so far, which is one of the crucial ones actually in SPH, is that we typically need some data structures to accelerate this. I hope you can imagine from the equations that I've showed so far, one key element is that we actually find all the particles that influence some particle j or I that we're interested in. Right? We always have these sums over I, and we actually now need to do this very often. We very quickly need to find for one particle or spot what are the particles around it, and this calls for an acceleration data structure. We actually go into this a bit more detail later for the collision detection. But the key point here is that we have something that very efficiently gives us the neighborhood of a particle. That's the first step. That's typically a big chunk of the computational complexity. Then we have a first pass over all the particles, evaluating all these kernel functions to compute the density, right? Remember the rho I values. And if we need it for surface tension, we could also directly compute this constant color field. With the density, actually for the color field we already need the density. Sorry, this would need to be a second pass actually. The density itself is definitely the first one. There we don't need it, and then for all others we actually need the density for normalization. And then we can go in and compute the forces for all the particles. So this is just basically computing the pressure force first, the viscosity first, and then, if needed, the surface tension force. This you know from mass spring systems, so by now you can just accumulate the forces. We have an accumulator for every particle, add them up, and then afterwards, once we have all the forces acting, gravity we might also want to add, then we can actually now move in and integrate positions and velocities. And then we could loop back and continue with the next time step. So note that all these pressure and viscosity values here, all these are per time step. We actually would not necessarily need to store these. They can be useful for debugging, of course, but they are fully recomputed in every step. One important note also, boundary conditions. We typically need some form of obstacles. The simplest one is a bit similar to mass spring systems. We basically clamp positions, right? We pose a wall or a floor by saying no particle can move beyond it. This has some drawbacks, because then you get a lot of particles that are exactly on that clamped position, and that can lead to clumps and some also stability problems often. What is typically better is to model this a bit more physically in this way. So we basically want to say there is no motion. We can definitely remove the velocity into the wall, right? Nothing should move through a wall. And then at a wall, if we have a particle also moving towards a wall, we can model the wall by exerting a counter pressure from the other side, like the wall region, that's exactly the same as the one coming in, such that as they move closer, we will basically have a growing number of particles and a pressure that pushes them potentially also away from the particle again, the wall region. For that, we actually need to really sample the obstacle region with additional particles. This is typically a bit more expensive, but actually in practice typically produces better results for the simulation. Yeah, so what's worth pointing out here is there is a kind of famous paper in 2003 that was the first one to propose these SPH simulations for computer graphics purposes. You can see one of their images where they actually show all the different particles here on this side, and then this is a kind of blurred visualization, or here they computed an actual surface covering these particles, which you can typically also get from something like this color field. And I do have a video, so this is actually now a video from that paper. So here it does not look that amazing, but yeah, this was the first work, and as you can hopefully now imagine, this was around 2,000 particles. Luckily, not all of them interact all the time, right? Then we'd have 2,000 squared for million interactions, but only neighborhoods. But nonetheless, for every one of these time steps, it actually causes a lot of necessary calculations, and in practice, the number of particles quickly limits what we can simulate for a given budget. Yeah, so let me discuss a few high-level properties of SPH. Nice point is definitely that it's a relatively simple method. The Navier-Stokes equations are really not that easy. They're a challenging model, and you can show that this SPH method in the limit correctly computes a solution for the Navier-Stokes equation. So in a way, that is a great property. On the other hand, we have this explicit integration, right? We're basically doing Euler steps for particles. Hence, it has stability problems easily. If you're interested, please try it out. It's still fun. It's interesting to play with, but if you do things wrong, it can definitely quickly blow up. A bit like maybe you saw with the mass spring systems. And I hope you also already saw we actually have quite a few parameters in the model, from this equation of state to viscosity to surface tension effects. And all of them influence the stability, so it can be difficult to get all of this under control. Yeah, so to mention one of the stability problems, especially if we have a lot of particles that basically cluster together in one position, which can unfortunately relatively easily happen from the explicit time steps. Right? If many particles move in to the same region, then we can imagine from all of these kernel variations of neighborhoods, we have a lot of overlapping particles here. And as a consequence, actually, we will get a very high density for the particle, especially the one in the middle here. Hence, we'll also get a very large pressure. And a large pressure here with a fall-off means we have a very large gradient, meaning the particles in this neighborhood, maybe especially this one, will actually get a very large force pushing it out of this region. And as I'm sure you know by now, large forces per time step with explicit time integration, that's bound to cause trouble. If I'm unlucky and too many particles go into one place, then this will blow up. Yeah, I've briefly mentioned that this pressure can also be negative when we have a density that's smaller than this rest density, and that can also cause problems. That actually has an opposite effect that kind of pulls particles back together, and that can sometimes also can lead to a bit unintuitive clusters of particles. Typically less critical for stability though. Another variant that I want to mention that's actually quite popular and unfortunately beyond the scope of this lecture, but it's actually quite a cool method, is what's called a position-based simulation. So the key change here is that we actually go a bit away from the force calculations and instead take the viewpoint to compute new positions for each time step. So we're trying to basically find the right spot for these particles, and then from these positions we compute the velocity by the change in position over the course of the time step, right? So basically from this we have a position t, then we compute a position pt plus 1, and then if you look at the difference of these two, right, so let me write it the other way around. If we look at pt plus 1 minus pt, that is the change within this time step, right, divided by delta t. Then, like a finite difference approximation, we can actually get the velocity of the particles, and then basically iterate that in a loop. And this has some interesting properties and can actually lead to more stable simulations. Typically called a position-based simulation method. There are also by now quite a few variants in that field. Yeah, we don't have time to go into the details here, but by now you should actually know about Navier-Stokes, SPH, how to compute the different steps, and also as a bit of a more fundamental topic, this difference between particle and grid-based viewpoints. And if you're interested on the slides, there are a few more links for further reading. And this is potentially a topic that can be interesting for the fourth exercise. Right, the third one will actually deal with the PDE topic, but for the free project later on, this is a popular extension. And with that, goodbye. See you next week.